Hey class, I promised you that I would make a video about null space, row space, and column space. So I did two different examples in the two different sections. So here I'm going to go through each of those examples and hopefully help to tie them together a little bit better. So some of this you should have already seen, but hopefully the beginning of this will also help to frame it better and talk about something that I should have talked about before, something we touched on yesterday actually, that should help to make sense of the relationship between the row space and the null space, and how they help us. So this picture should look familiar up here. So this is what we talked about yesterday, and this is one way to think about a basis. There are different bases for any subspace, and given a basis, you can get there's exactly one way to get to any point. Given a basis, in this situation, we could go a negative 1x and up 3y, or that's with these two directions as your basis. But with u and v as your basis, you would go a negative 1u and then 2v to get to that, to make w, or to get to the point here that's at the end of w. That kind of thinking we are going to use because we will use directions in the row space and null space instead of the standard basis to get to a point, and then we'll find that the movement in the null space direction doesn't matter, and really all it matters is where we are in the row space. The other thing that will help us out is to think about this ax equals b. These are x and b are vectors here. They can be thought of as a function, so we're going to be thinking about inputs and outputs. And inputs, x is our inputs, b is our outputs. And you've been taught when you've worked with functions about the values you can input into a function is called your domain, and the values you get out are your range. And with these linear functions that we work with, there's no restriction on the input. If we have things like the square root of x or 1 over x plus 1, then there are restrictions here. Like mathematically, we just can't do that in the real numbers. We can't input negative values into the square root of x, and we can't for x. We can't put in negative 1 in for x in this situation because the denominator will be 0. We don't have those kind of restrictions when we're dealing with matrix multiplication because all the linear combinations are really nice. There's no mathematical restrictions. We're more in this situation like this, y equals x squared, where here you can put in any real value. There's no restrictions on what you can put in there mathematically. But what we get out, like here, y will always be greater than or equal to 0. So, so here we're kind of restricted in our range, but we're not restricted in our domain with the input. And the column space, we will see the column space corresponds to the range, like that's like where we can end up after the multiplication. So with that little introduction, I'm going to pull up a, here we go. So we're going to start off with something very simple, ax equals b, where we just have 1, 2. Oh, I wrote it as a row vector instead. Oops. I did want it as a row vector, but I shouldn't have put that. I shouldn't have put that comma right there, so I apologize. It should be 1, 2 without the comma. So, so we're thinking about this. We can think about, hey, I have two foods. One has 1 gram of fat per serving. One has 2 grams of fat per serving. We can think about that as the context we're working with. And the row space, that's just the span of the rows. And in this case, there's only one row, so it's the span of that. The vector, the row vector 1, 2, I can represent with this. It's u. the span of that is this whole line. Okay, so this is our row space, is this line. It's all possible linear combinations of the rows of our matrix. In this case, we only have one row, so it's the linear combinations of that. Since we only have one, the only linear combinations we can do is a scalar multiple. And so we just get the stretching of that line, of that vector, so it makes a line. So one question we get asked in this situation is, what values, so if I think about this as x, let me pull up the pen. If I think about this as x times 1 plus y times 2 equals 0. So what are all possible combinations of x and y where that make this 0? Well, 0, they could both be 0, so we've got that, the origin there. But there are others. For example, I could take a negative 2 for x and 1 for y. So a negative 2 for x and 1 for y. So right there, that's one possibility. I could take 2 for x and a negative 1 for y. I could take like 3 for x and a negative 1.5 for y. So I've got some options, and if we look at all of that, they fall on a line. So all of the let me put a vector on there. So let's do a negative 2 comma 1. Oops, let's do 1, 2 comma negative 1. I'll take that as my vector. Any combination of this, any scalar multiple of that vector, it's going to not going to change the amount of fat that we have in our diet. If we change by those things, we'll get 0 out. If we're not eating anything now and we change it by those values, we're not going to get anything out. So if we increase the serving of food, the first food by 2, and drop the serving of the second food by 1, then we're still not going to be changing the amount of fat in our diet. I think I said that incorrectly to begin with, but yeah, we're taking some fat. This will talk about the change of our fat in our diet. So the span, oops. Yeah. So that vector v is a vector in the null space, and the span of that vector, since in this case we only have a one-dimensional null space, will be a line. So this line that is made by the span of v, that's our null space. This 1 by u is our row space. And I may have mentioned this before. I think I mentioned in class, like all of your input space can be described as part of your row space and part of the null space. You might be saying, well, but Brother Corey, that's not everything. You just have 2 lines. There's a whole bunch of spots out there that I can't get to. Well, we'll come back to that. So if I am at 3, how about 3 and a negative 1? So let me put a point there, 3 comma minus 1. How does that change my, how does that change the amount of fat I'm going to have in my diet if x is 3, y is a minus 1, or I increase the servings of the first food by 3 and I decrease the second food by 1? Well, we're going to get 3. Oops, I have to go back to my pen. We're going to get 3 times 1 plus a minus 1 times 2, which is going to be a total of 1. Okay, so so if those are my inputs, that 3 a minus 1 is my input, I get out 1. I'd increase my fat intake by 1. Well, there are other points that I could take that also would increase my fat intake by 1. Can you find one? Well, 1, 0 is 1. Right? If I make x 1 and y 0, 1.1 plus 0.2, then I get out 1. So I've got this spot right there. A minus 1 and 1. So like if I have this 2 and I subtract that 1, and I can get that with a minus 1 times 1 plus 1 times 2, that's 1. And so I have that spot right there. And those also look like they're all on the same line. So there. Look, and they are. And that line is perpendicular to the row space. Also, if you didn't notice, the null space vector was perpendicular to our row space. Okay, so here's where here's where the thinking about a different basis or different directions helps us a little bit. I can go. Sorry, I have to pull out my pen again. So instead of thinking about getting to A as coming along this, going down up 3 and over A, then I can think about going up in this direction along U and then going down along this direction to get to A. But movement in the V direction, that's part of the null space direction, and movement in that direction doesn't change anything. Really, all the important information is about right here. It's just where I am. It's how much in the row space direction, where I am in the row space, or the projection of A onto the row space. We could do the projection formula to figure out what the vector 3 a minus 1 is projected onto the vector 2, 1. But we can also have GeoGebra just find out where the intersection of those two lines are. If I remember, F and H. Okay. And that is 0.2 and 0.4, or 1/5 and 2/5. So the only important thing, the only thing we really care about in this situation, or what the output will be, the only important part of A on the output is that it's 1/5 and 2/5, or 0.2 and 0.4 in the row space. And it doesn't matter that it's been moved over here in the y direction. Any point on that row will be, on that line, will be the same as just having a serving of 1/5 of the first and 2/5 of the second. And so what we have is we can think about any point in there as some value. We'll call it C. Oops. C times the row space vector plus D times the null space vector. So any point, I can think about it this way. That's thinking about it's thinking about a new basis. So I can think about not thinking about x's and y's and thinking about how much of u and how much of v. So I can write that as any point. Any x, y you give me, I can write it out that way. Maybe we should do it this way. See, the row space basis is 2, 1, and the null space is 2 and a minus 1. Oops, I made a mistake. Oh, dang it. It's 1, 2 over here. Don't even know how to erase with this. Okay. So any x, y you give me, I can write it as so much of 1, 2, and so much of 2 and a negative 1. But when I multiply that by a, this part will go to 0 because it's 2 minus 1 times a is 0. So this part goes to 0. So really all that matters is where I am in the row space, how far I go in the row space, or the projection of the points onto the row space. Okay, so any point I pick, I can think about, oh, so much in row space, or in the row vector, so much in the null space basis vector, and it really doesn't matter. This part doesn't matter. I just have to think about, oh, where I am in the row space. How much of the row space I needed, how far I traveled in the row space to get to my point here, because the movement in the null space isn't going to change the value. Okay, so and in general, this is how it works. And the meaning, like the input space, you can think of any point in the input space as row space, the coordinate in the row space plus the coordinate in the null space, and it turns out the coordinate in the null space doesn't matter in terms of your output. It's really only the coordinate in the row space. The row space might be a plane. The row space, it might be that the null space is just 0. If the columns are linear or the rows are linearly independent, then the null space is just going to be the 0 vector. So so the row space is everywhere. Okay. So one of the things we've learned is that the null space is the basis for the null space is perpendicular to any vector in the row space. And let's go look at a higher dimension example here. So this is, here I have an example. This is right from a class. I gave you guys this matrix. You're supposed to find the row space and the column space of it. Oh, I forgot to talk about the column space in this other example. So what's your column space? We only get out one number when we do ax equals b, because we have a 1 by 2 and a 2 by 1. We only get one value. So the row space is just going to be one-dimensional. And sorry, I made a mistake. The column space is only going to be one-dimensional. We can think about it as it's just going to be one value on the x-axis down here. So, and the dimension of the row space and the dimension of the null space are always the same. So since the row space is just a line in R2, the column space is just going to be a line in R2. So yeah, if the row space was a plane, the column space will be a plane. Okay, so let's go here. So in class, we figured out what the row space was and the null space of this. And the row space, these two rows are linearly independent, and these two black vectors are those two row vectors. And so the row space will be the span of that. Span. Looking for my plane here. Oh, there we go. Okay, so the span of that row space is that blue plane. So that is the row space. The span of those rows is that. If we row reduced, I claimed in class that it doesn't matter if you row reduce and then take those columns. So here's the row reduced echelon form. You can row reduce and still take those new rows, any of the rows. You have to take all of the rows that have a pivot position. In this case, both of the rows have pivot positions. The span of those should be the same as the span of the rows that have a pivot position in the original matrix, which happen to be both of them in this case. And if we to go find a few more vectors here. So these two vectors, those two red vectors there, they are the reduced row echelon vectors, and look, they lie in the plane, and they're linearly independent. The span of those is the same as the span of the originals. Okay. Well, what about the null space? Well, the null space is always perpendicular to the row space. So in this case, since we're in R3 and the row space takes up 2 dimensions, the span of the row space is 2 dimensions, then we have 1 dimension left for the null space. And so that 1 dimension, there's my null space vector. So that 1 dimension here, it's going to be a vector that goes perpendicular to that plane. So that's the null space. So if I have any point in R3, I can think about this point. You can ignore that other point floating around the back. I can think about any point in R3 as being having a coordinate in the row space and then going perpendicular to the row space to the null space. Like I could drag this one over here, right? So then my null space vector, the coordinate in the row space would be 0, 0, because I'm at the origin, and then the null space would be 1 null space vector. And the reason that's helpful is because the most important information is that I'm at 0, 0 in the row space. So any point that's on the line that would be spanned by that null space vector, that is, they would all have 0, because moving in the null space direction doesn't change anything. So, oops. Or if I came up over here, then I could move. I lost my point. Get rid of some of those traces. There we go. So, let me move it back over this direction. Okay, so there's that L. If I look perpendicular like this, maybe, oops, it's not going to be exactly right. There we go. So the coordinate, the spot where that looks like it is in the plane, if I project it back onto that plane, those 2 coordinates are going to be the most important coordinates, because the movement out of that plane isn't going to change the value of L when I multiply it by A. So if I could move this, if I was very good at moving this in that dimension, then that point in the background shouldn't change. So that point in the background, as I move this along, that is the vector A times the vector L, like this point here. If we drew a line from the origin to L, then what I get out is that point that's moving around in the background there. So, but notice where that is. Notice all of those points in the background, they all lie on the XY plane. Remember, I just claimed that, hey, any point in the row space, the column space is always the same dimension as the row space. This is a 2-dimensional row space, and so we're only going to end up with 2 dimensions in the column space. So we get this new plane right there as our output. We're only going to get x's and y's in our output, and that makes sense here since we only have two rows. When we take linear combinations of those columns, we're only going to get an x and a y coordinate out, and it looks like we can get any point, any xy coordinate out here, and we can. Okay. Well, I hope so. Now you've at least seen 2 examples here that talk about null space and row space, and column space is our output space. It's kind of like the range when we think of a function. So not as much in like the how to find this. I think that you guys are more confident in how to find the basis for the null space, how to find the basis for the row space. This is more like conceptual about what's going on here. So this is the row space. Since this is this is a 2 by 3, the inputs are going to be in R3. So any point in R3 is going to be an input, but my outputs will be in R2. And since I only have 2 pivot positions, my row space will be 2-dimensional, and my column space, my output, will be 2-dimensional. So hope that helps a little bit.